Okay, so this morning's lesson we're starting C3 chapter 3 and it's called Exponential Growth and Decay. Some of this is new stuff and some of this is stuff you've actually seen before, even though it may not have had this title. So if you want to put the title down, C3 chapter 3 Exponential Growth and Decay. Yeah, it's a 4th of the 7th, 13. Can anybody tell me, first of all, you've already sort of had a clue in the title here really, what do compound interest and bacterial growth have in common?
It grows rapidly, like it doubles each time.
It grows rapidly, it might double each time. If only interest in the bank doubled each time, that would be wonderful. Yeah, it might not double, but it goes up the same sort of proportion each time. Yeah, okay. So, let's look first of all at compound interest, which is something you know about from GCSE. And just see what we can get from there. I'm going to change the lighting here, see if that's any better. Okay. So let's say to start with, for our compound interest example, to make things easy, that we're going to invest £100 at 10% per annum, so per year, and it will be compound interest. Then I'm just going to draw up a little table. We're going to have time periods and we're going to have amounts of money. At the start, we'll call our time period time 0. So at the very start, and that'll be common to what we're doing in this chapter if we're doing things with time, initially, so this is like the initial period in time. Initially, when time is 0, we have £100. 1 year into things, how much money do I have? And I don't actually want an answer, I want a sum that will tell me how much money I will have. Tabby?
100 times 1.1?
Yes, okay, that's right. That's how much money I will have. If it's 10% each year, 10% as a decimal is 0.1, so you always add 1 on to that, so that's where that 1.1 comes from. So by 100 times by 1.1. At the end of 2 time periods, can somebody else tell me what sum I could do then to know how much money I've got at the end of my second time period? Yep.
Would it be 100 times 2? Or that's just a guess?
Yeah, that's not correct. The 2's in there somewhere, but it's not there. Yep.
Is it 1.1 squared?
Yes, it is. That's right. Okay. Because it's 100 times by 1.1, which was what we had here, times by another 1.1. So that's why that's in there. So for time period 3, Eve, how much money will I have after 3 time periods?
100 times 1.1.
Yep, that's right. And in general, after n years or n time periods, Leon, how much money will I have after n periods of time?
100 times 1.1 power then.
Yeah, that's right. 100 times by 1.1 to the power of n. What you've got here is a number, which I'm going to call A, times by another number, which I'm going to call B, and then I've got my n up there. And that is the model we use for exponential growth. And here is amount of money, so I have M here maybe for money, was A times by B to the power of N. That was our model for this compound interest thing. As far as we're concerned and what we're doing, well, what happens if B is greater than 1? I want you to think about what happens if B is greater than 1. And I want you to think what happens if B is between 0 and 1. What happens if B is greater than 1? What happens if B is a 0 point something number? So here my B here is my 1.1. Yep?
If B is greater than 1, does it increase?
Yeah. If B is greater than 1, it increases, and what we get is what's known as exponential growth. So what happens if b is a 0 point something number? If b is between 0 and 1, what happens then? Someone said it? It decreases, yeah. And that's known as exponential decay. So it might be radioactive particles are decaying over time. That's exponential decay. So we've had a quick look at a compound interest example. This thing here, this model, was quite important. The general thing is you've got it's equal to something times by something to a power. Just before we go any further, this A, this number here, can anybody sort of describe in words then what this A is? If you look back at the original question, what's this A? Yeah, A is the initial amount, that's right, okay. So A is the initial amount. And B is, well, if I just call it the multiplier, it tells us basically how much it's going up or down each time. So we've got A is the initial amount and B is the multiplier. And here, N would have been the time period. And it usually is time, so often that letter may become a T for time or something like that. So we're going to have a look at another example now based on bacteria quantities. And this time I'm going to give you some amounts and some time periods. We're going to have time period, denoted by T, and we're going to have the amount of bacteria, denoted by N. And I'm going to tell you that in time period 0, so at the very beginning, we've got 2,500 bacteria. Or that might be the area in millimetres squared or something, I don't know. But that's the amount of bacteria we have. One time period later, we've got 3,250. After 2 time periods, we have 4,225. And after 3 time periods, we've got 5,493. So we can see we have growth. And what I want to come up with here is, given that there is exponential growth here, so given exponential growth, I want to know what's the model, what's the formula, in other words, what's the model or the formula for this growth. And I also want to know how many bacteria there will be and the 10th time period. So how many bacteria when time equals 10. So that's sort of the question. So if we look at the model we had earlier, yep. Yep. If we look at the model we had earlier, we had some letter, well, I'm going to have my N over here for the number of bacteria, because it doesn't matter what letters we use, is equal to some initial amount, which I'll call A, times by some multiplier, which I'll call B, and then I'll have T as my time period. So that's going to be my model. That is my basic model, which I'll come back to time and time again, for exponential growth or exponential decay. That's an equal sign there. So I've got to try and work out here what A is and what B is. So can anybody tell me what A or what B are? Can anybody tell me one of those things straight away?
B is 1.3.
B is 1.3. So hang on, let's have a look. Finding B. What did you do to find B?
I divided time 1 by time 0, so 3,250.
Okay. If you do one amount divided by the previous amount, okay, did that come out to be 1.3? Okay. So that was effectively, if you want to call that one there N0, that one N1, that one N2, and that one N3, what you've just done then is N1 divided by N0. Now if it really is exponential growth, that should happen all the way through. So let's just do a check a minute. And if we divide another pair, so if we divide N2 by N1, let's see what we get then, N2 by N1. That would be 4225 divided by 3250, and hopefully that is also 1.3. Has anybody done that to check? It is. Tabby's nodding. That's 1.3. Okay, because that should be constant. Okay, B here is the same each time. Okay, so B should be constant if it's exponential growth. So I now know then what my B value is in my formula. B, my multiplier, is 1.3. Right, can anybody tell me, if I zoom out so we can see the whole table, what in this model, what's A? So that was finding B. If I want now to find A, how will I go about finding what A is? We said earlier what A was, we should have written it down. Bethany? It's 2,500, yeah. A is the initial amount, the amount that we start with, okay? So A, it's the initial amount, it's the amount at time 0, so A here is going to be 2,500. So then, we have our model, or our formula. It's often called a model if you're trying to model something in mathematics. And our model we wrote down earlier was n equals AB to the t. Well, now I know what A is. A is 2,500. And I know what B is. It's 1.3. So there is my formula to model the growth of these bacteria. I'm going to do the rest of the question in a separate video.